kind of can use one quick observation. Okay? So remember, this says that df dx equals t. And so if we want to take the derivative with respect to y of df dx, well, that would just be the derivative of t with respect to y. Okay, so what that would be the second derivative of f with respect to y and with respect to x. And that equals the derivative of t with respect to y. And likewise, we also know that df dy equals q. So if we want to take the derivative of this, now with respect to x, well, that's just going to be the derivative of q with respect to y. And so we're going to have the second derivative of f with respect to x, and then with respect to y, it's going to be equal to dq, and that's just to be a dx. So we took the derivative with respect to x. So this is going to be dq dx. However, we also know that those two are equal, thanks to Claro, maybe I'm going to spell his name right, Claro. And so if those two are equal, then what that tells us is that these two have to be equal. And so we actually have this neat little theorem. And it looks like this. And this is the big one. This is the kind of nuts and bolts of the theorem. And so it says that if we have a conservative vector field where P and Q have continuous first order derivative, then this statement must be true. And so therefore, if, on the other hand, dp dq, or dp dy is not equal to dq dx, then we know f is not conservative. So all we have to do is kind of take the ith term, take the y derivative, and then take the jth term and take the x derivative, see if they're equal. Pretty straightforward. Going the other direction is definitely harder. We have to kind of add a couple little definitions on V, and I'm not going to really bog you down with those right now. All simply connected means is no holes. And so maybe if I show you some examples. Okay, so like that would be simply connected. Whereas each of the following fails to be simply connected. So we could have something like if we want this region here and throw out kind of this hole in the middle, then that fails to be simply connected. Or if we have kind of this break in the middle, that also fails to be simply connected. So all simply connected means is it doesn't have any holes, no gaps. It's just kind of one solid piece. And we can actually go through and show if the simply connected region, if we're on a simply connected region, and this is true, then therefore F must be conservative. So that's kind of the converse. Before we have, if it's conservative, then this must be true. And this tells us further, if it's simply connected, and this is true, then F is conservative. Okay, and so we kind of have to go in both ways. So this is really the big thing here. This is how we're going to be testing. Okay, to find out if things are simply connected, or to find out if this vector field is a conservative vector field or not. Which all that means again is that it can be, we can write it as the gradient of another function. Okay, so I just want to go through a few examples now of how to put this to use. Okay, so let's determine whether or not this is conservative. Okay, so we know P of xy equals x minus y, and Q of xy equals x minus 2. Okay, so the derivative of P with respect to y is just going to be 0 minus 1. And the derivative of Q with respect to x, well, that's just going to be 1. And so these are not equal, and so we know F is not conservative. And it's that easy. We just check those partials. As soon as they come back telling us they're not equal, then we know they're not equal. And we know it's not conservative. Okay? Let's take a look at this one. So here, P xy equals 3 plus 2xy, and Q of xy equals x squared minus 3y. So when we take the derivative of P with respect to y, I think we can get just 2x. And when we take the derivative of Q with respect to x, well, we're also going to get 2x. And so these are equal. I mean, they're not, but they are equal. These two are equal, and so therefore, all we have to do is test to see if they're equal or not. Okay, so we saw an example where they were not equal, it's not conservative. An example where they are equal and it is conservative. Let's look at an example of how we can cook up maybe what that gradient function is going to be. Okay? So we want to find this function f such that the gradient of f is going to be this force field, this vector field, big F. Okay? And so what that tells us, well, we know that P of xy equals 3 plus 2xy. But we also know that that equals the derivative of f with respect to x, and Q of x y equals x squared minus 3y squared. And we know that that equals dx dy. Okay, so let's kind of pretend this is equation 1 and this is equation 2. And what I want to do is I want to integrate equation 1 with respect to x. Okay, so we have df dx equals 3 plus 2xy, and we want to integrate that with respect to x. And so over here we would just get f, and that would be equal to, well, we're going to have 3x plus x squared y plus some constant function that only has to do with y. The reason that comes up is because when we differentiate with respect to x, that'll just go away. Okay, so this is what equation 1 turns into. And when we integrate equation 2 with respect to y, so now let's do the same thing. Now we're going to take df dy equals x squared minus 3y squared, and we're going to integrate with respect to y. So here we're still going to get just f, and we're going to get x squared y minus y cubed plus some function, maybe we'll call it g, not g, we'll call this one g, and that's just going to be independent, just depend on x. Okay, so in other words, we know that f equals 3x plus x squared y plus some function of y. And we also know that it's equal to x squared y minus y cubed plus some function of x. We'll notice we have the x squared y in both of them. And so our function of x, well, it must just be 3x. Those two are connected. And our function of y must just be negative y. And so f of xy just equals 3x minus y cubed plus x squared y. And then, because we don't really know, we're going to have some plus c out here because we integrated, but we don't really have to worry all that much about that. Okay? And we can confirm, just to make sure, let's see what delta f equals. We know when we take the derivative with respect to x, in our first component, we're going to have 3 minus 3y squared. No, I lied. Taking the derivative with respect to x. So we have 3 minus 2xy. And we take the derivative with respect to y, we're going to have negative 3y squared plus x squared, which we can confirm absolutely is equal to x from the beginning. 3 plus 2xy, and then x squared minus 3y squared. Okay? And so, now to evaluate this line integral, we want the integral along C, where C is given by this vector function r of t equals e to the t sine of t, and e to the t, and e to the t cosine of t. Okay, but we already showed that f just equals the gradient of little f from right here. And now we can just use the fundamental theorem of line integrals. So it's just going to be f of the endpoint minus f of the initial point. Okay? So t, I forgot what t goes between. T goes between 0 and pi. And so the endpoint of this, if we plug in pi, well, sine of pi is just 0. And so the x is going to be 0. And the y, cosine of pi is negative 1, so I think it's going to be negative e to the pi. And then when we plug in 0 to get our kind of initial point, that's going to be 1 times 0, so that's going to be 0. And then e to the 0 is 1, cosine of 0 is 1, so I think it's just be 0, 1. So I think we're just going to be going from 0, negative pi down to 0, 1. Okay? And so all we have to do is just plug these into our functions. And so when we plug in 0, negative pi, we're going to have 0 minus negative e to the pi cubed plus 0. And then we have minus, and we have to plug in all of this. I think we're just going to have 0 minus 1 plus 0. So it looks to me like it's going to turn into e to the 3 pi plus 1. Okay, I'm going to go through one more example. It's kind of the same thing, but now let's look at in 3 dimensions instead of 2. Okay, so here we have the f dx. That's going to be our p of x, y, z, and it looks like that's our I component. So that's just y squared. And then the f dy is going to be our q. And so that's going to be qxy plus e to the 3z. And the f of z is going to be that r, that k component, which is going to be equal to 3y e. So now we kind of have 3 functions, but we're going to do the same thing. So when we integrate, well, we have 3 equations. When we integrate the first one with respect to x, we're going to get f equals the integral of y squared dx, which is going to be equal to xy squared plus some function of y and z. Again, because we just integrated with respect to f on x, so y and z would kind of fall out. Okay? We also know that f is going to be equal to the integral of 2xy plus e to the 3z dy, which is going to be xy squared plus y e to the 3z plus some function x and z. And finally, when we integrate the third one, we're going to integrate 3y e to the 3z, with respect to z, and I think we're going to get y e to the 3z plus some function, we'll call it k, and that's going to be a function of x and y. So what we're going to have to do is inspect to figure out which pieces are going to kind of hang around, so we can kind of compare these. So this came from 1, this came from 2, and this came from 3. Okay, so if we compare 1 and 2, we notice that we're definitely going to have x squared plus y squared. I mean, just x, y squared, I don't know why. We're going to have x, y squared, and then we have some functions of y and z, and so it looks like maybe that's going to be y e to the 3z. And then again, we're going to have some arbitrary constant. And that's going to do it. That's going to give us our function. So in other words, all we kind of have to do is isolate our components of our vector field and integrate them kind of with respect to whatever component they are. And then kind of by inspection, we see, okay, we have that. We're also going to have that. But notice that x, y squared can be this function k of xy, which is this function of xy. And that function y e to the 3z can be our function g of yz, because that's the function of y and z. And so our function h, in this case, ends up just kind of being theorem. Okay, and again, we could go through and verify that the gradient of this function is going to be exactly that 4. Okay, so that's it for the fundamental theorem. I just want to very briefly kind of take a look at kind of some physical implications, just because this is kind of